I'm Sarolta Laczó, and so this is joint work with Johannes Gierlinger. And needless to say thanks to the organizers for having us. So this paper, we read a lot about risk and limited commitment that Kostas already talked about just before me. But this is a theoretical paper, so I'm not going to generate any numbers to match to the data or anything like that. Okay? All right, so basically in this paper, we think about household decisions, and we focus on one role of the household, which is providing insurance. Okay, we think about the household as a risk-sharing institution. If income shocks or some health shocks or other shocks are imperfectly insurable, so basically they are incomplete markets, then the family can serve to provide additional insurance. Okay? And so this motive for household formation has been emphasized in the literature. For many years I've put some sort of older papers, and of course there are many others who say that this is one important motive for household formation. Okay? So what we'll do in this paper is try to determine who should marry whom, okay, who should match with whom for purely this risk-sharing motive. Okay? And so more generally, you can think of that if risk-sharing doesn't occur in the whole community but in some subgroups, we would like to know what would be the composition of these subgroups. Okay? And while we simplify the analysis, in that these subgroups will be couples. Okay? I'll get to that in a moment. Okay? All right. So before that, let me say what is our starting point. Okay. So we'll consider a marriage problem. Okay. So what is a marriage problem? So there are two sides of the market. Okay, men and women. And this will be one-to-one matching. Okay. So couples will share risk. Okay. And utility will be imperfectly transferable. Okay. So within the couple, consumption can be transferred one-to-one, but clearly utility cannot be transferred one-to-one. Okay? And we assume that on the marriage market there are no such frictions. Okay? And so this is the framework of Chiappa-Orientani and Legros and Newman. Okay? And so what is the main issue that we are dealing with and that these papers were dealing with is to characterize the associativeness of couples with respect to some attribute. Okay? In particular, we, and just like Chiappa-Orientani, will focus on risk aversion as this attribute, okay, of agents on both sides of the market. Okay? So what is the result of the existing literature? So is that the stable matchings that I will define precisely later, so basically that no two people would want to deviate and marry themselves. So these matchings will be negative associative. Okay? So what this means is that if you take any two couples, okay, the more risk-averse man is matched with the less risk-averse woman. Okay? And vice versa. Okay. Now let me try to say something about why we care about matching. I mainly focus on the family application, but then there are other applications of this theory. Okay? So, well, first of all, it has been argued by Mazzocco, for example, that to know the risk attitudes of spouses within the household is key to link individual preferences to decisions at the household level. Okay? He focuses on the consumption saving decision. You can think about portfolio allocation decision. So if you want to start from individual preferences and say something about decisions of households on average in the economy, so at the aggregate level, we should say something about actually who is in a household with whom. Okay? And then my second motivation is borrowed from the paper of Chiappa-Orientani. So in the empirical literature, if we look at household data, then we implicitly assume often that actually household members have identical preferences. Okay? So this is kind of how we can link individual preferences to the observed outcomes at the household level. Okay? And then there is more recent work arguing that that the change in education of women, so the increase in the share of women who go to college, can be linked to what we call a marriage college premium. So basically, you go to college to find better partners to marry. Okay? So also in that decision, later matching would be important. Okay? So there are many other applications when we think about two-sided one-to-one matching that I'm not going to talk about today. So you can think about matching projects to managers or workers to firms, okay? Or workers in a team, joint ventures, or sharecropping agreements. So in all these cases, when we want to think about who would, for example, enter into a joint venture, which firms, they have some attributes, we can say something about the sorting pattern. Okay? Right. So, and what we do more precisely in this paper, so we start from this static matching to share risk framework of Chiappori and Rennie. Okay? By static, I mean that there is a matching stage and there is one period where these matched agents will share risk. Okay? And we would like to study whether the negative assortative matching result of the literature is robust to two extensions. So one is that we introduce dynamics. So basically there will be repeated interaction after the matching stage, so in the risk sharing stage. And we allow for limited commitment, in other words, separation or divorce. Okay? And where I cited Koshel Lakota, there could cite many other people, so Thomas Ermolhol in particular. Okay. Okay. And so I will not keep the suspense, so we will show some conditions under which positive assortative matching emerges. All right. Okay. So why I introduce limited commitment and not some other friction starting from the existing literature? So well, first of all, as was mentioned already in the previous talk, so limited commitment generates partial risk sharing. Okay? And in particular, now we are interested for within the household. So again, there is evidence from the US by Mazzocco, who shows that intertemporal decision of couples can be better accounted for if we allow for limited commitment. So he tests limited commitment against perfect risk sharing within the household using the CX. And there's also evidence from developing countries, so in particular from Ethiopia, by Derkon and Krishnan, who also find that households do not share risk perfectly. Okay, so members of a household do not share risk perfectly. They don't have an explicit limited commitment argument, but they also say that one determinant of what happens within a household is divorce, and so what happens after divorce. So this is, we can also think about this as limited commitment friction. Yeah? And more broadly, we would like to argue that this limited commitment friction is relevant whenever we think that these matched agents will interact repeatedly, okay? And quitting is an option. So if two firms have a joint venture, if there's some interaction over time, again, we could think about this limited commitment friction. Okay, so that then if there are no questions, then let me turn to the math.
I'm sorry, the matching occurs only along one characteristic?
Yes, yes. So the one characteristic, we focus on risk aversion. It can be translated one-to-one to, for example, difference in wealth, if then the sort of additional risk is the same. So there are other ways of saying it, but we will say that it's risk aversion. And you will see that already like this is complicated. So if you have multidimensional heterogeneity, that would be quite intractable. All right, so there are two types of agents which we call men and women. Okay, and for simplicity, we assume that there are n of both types, and we will index them in the following way. So women will be indexed by I and men by J. Okay? We consider IID risk, again for simplicity, and to have some analytical results, for now we'll assume that there are only two states of the world, okay, that we will denote as upper bar and as lower bar. Okay? So it's an endowment economy, so women will have this endowment process, cap W, okay, so they receive LW upper bar in the state S upper bar, and so on. And men's endowment is denoted cap M, and then we denote by Z the aggregate endowment. Okay? All right. And then, as I said, the heterogeneity is in risk preferences. Okay? And so we will use our index to say something about who is more risk averse. Okay? So an I double prime woman, so you can say Miss I double prime, is more risk averse than Miss I prime. Okay? So and this notation will mean that she is more risk averse in the arrow pair sense. Okay? So Miss I double prime has a more concave utility function than Miss I prime. Okay? And similarly for men. So I just wrote it as this is the total endowment, and then we can write the men's as the total minus the women's endowment. Sorry?
Does the women's share in marriage?
No. So this is you can think of it as income. So this is what they are endowed with, and from then they can make transfers, and consumption will be determined.
The risk hits the household simultaneously. They're not at independent jobs. Am I mistaken?
You can. So this is kind of general. So written as such, we can have perfect positively correlated, negatively correlated, or no correlation between income. So if for example Z is constant across the two states, so there is no aggregate risk, then incomes are perfectly negatively correlated. But we could have that. I don't know. This is always 4 and 2, and the men's is also 4 and 2.
So
The same state.
Z upper bar and Z lower bar, also high Z and low Z necessarily.
Yeah, I mean, of course, it's without loss of generator to have like this higher than that, but yeah, it could be any number for now. Okay, so and there's a common discount factor that is beta, okay? And we assume, as is standard in most of such models, that the outside option is autarky. Okay, so in other words, being single. Again, in other words, we assume that there is no remarriage, so there is a trigger strategy. So if somebody would deviate, that person would have to stay single forever. All right. Now, let me show you the timing. So there is a time 0 stage, okay, where matching takes place and there are no search frictions. So we want to think about what should happen. So what would be the efficient way to match? Okay? And then from time 1 to infinity, the following sequence of events follows. So first the state is drawn, okay, this has upper bar, S lower bar, and this state is observed by all agents. Okay, there are no information frictions in our model. And then each agent may decide to make a transfer, okay, if matched. Okay. However, it is possible that the agent chooses, well, not to make a transfer. Okay, so the agent who is lucky today might decide that he or she is better off in autarky or being single. Okay? In other words, there is unilateral divorce. Okay? And then finally consumption takes place. Okay, that's all that happens in the model.
Why do people marry other than risk sharing?
There is no other reason at all.
Okay,
So it's
all into
yeah. So it's so the simplest possible way we focus on just one motive for household formation.
So the only difference between Thomas and Morale is the heterogeneity in risk aversion.
Yes, so at this stage, yeah, exactly. So at this stage, you can think of it as Thomas and Morale. I mean, the qualitative characterization is the same also. You can, if you don't have symmetry, it's just like slightly more difficult to solve. It's basically the same. So what we really add to that is the matching stage. All right. Okay. So then let me define now our objects of interest, which I already mentioned that we want to think about stable matchings. So now I want to define this very precisely. Okay. So and to define that, I need two more things. So first of all, we say that a couple is individually rational if both the man and the woman prefer to be in the couple than being single. Okay? That's one thing. And the second thing, is to define what is a blocking pair. Okay? So suppose that there are two women and two men matched. Okay? It cannot be then the woman of one couple and the man of the other couple would like to be together rather than be in their current match. Okay? That would mean that this couple is a blocking pair. Okay? Right. And then we say that the matching is stable if all couples are individually rational and there are no blocking pairs. Okay? So then we will want to say something about these stable matchings. Okay? And so as in the literature on so the static marriage problem, we will be interested in assortativeness of these matchings. So, well, then we give you the precise definition of this. So we say that the matching is positive assortative. If we take two couples, ij and then I prime j prime, if we know that with our previous notation that j is more risk averse than j prime, then this will imply that I is also more risk averse than I prime. Okay? In other words, matching is positive assortative if for any two couples the more risk averse man is matched with the more risk averse woman. Okay? And negative assortative is the opposite. Okay? And then we'll call two matchings payoff equivalent if the level of expected utility is the same for both matchings for every agent. Okay? This we need for a limiting case. Okay? And then we say that the economy satisfies positive assortative matching if each stable matching is payoff equivalent to the positive assortative one. Okay? And similarly, we can define an economy that satisfies negative assortative matching. Okay? All right. So, so the whole aim of the game will be to see what are the characteristics with respect to assortativeness of stable matchings once we introduce limited commitment. Okay? And to do that, we will make use of sort of an old concept in risk theory that I'll
The last statement says, you know, I have an economy, I can reshuffle these people and create a positive assortative making, I will get the same expected discount for all the agents, and I call the initial economy satisfying positive assortative making. Is that right?
Exactly.
Okay.
Exactly. So this is irrelevant when you get to perfect risk sharing, which in this model, if the discount factor goes to 1, you get to perfect risk sharing. And if there is no aggregate risk at all, basically, so all matchings could give the same utility to everybody. You can basically reshuffle agents. So this is to take care of the limits, and it's under very narrow conditions that it's important that, well, if basically you can reshuffle agents and everybody will be just as well off. Yeah. All right. So now let me introduce, well, not introduce to, like, remind you of what Jewitt's order is. Okay. This is to kind of try to explain then how we get the results. Okay. Right. So why we need this? So we would like to rank lotteries. So lotteries will be basically the consumption lotteries. Okay, there will be some risky consumption in this framework because of the partial insurance within the household. Okay, and we would like to say something about the riskiness of those lotteries, even when agents disagree on which lottery they may prefer. Okay, why this is interesting, because sorting in this framework may work by agents actually disagreeing on the attractiveness of a partner. Okay? You may think, of course, if everybody agrees on the ranking of, say, men, okay, and similarly for women, okay, then sort of the most attractive ones will match. This is actually Jan Eckhout's result from 2000. So then it's kind of a, let's say, an easier case. In this risk sharing framework, you will get cases when this is not true. Okay, that not everybody will agree on the attractiveness of partners, and this is also true in the perfect risk sharing case, not just with limited commitment. Okay. Now, so one more thing: why we need Jewitt's order, and why, like a more standard second order stochastic dominance measure for riskiness is not enough. Is that again there that means that all risk-averse agents agree on which lottery is less risky. Okay? So then what is Jewitt's order? Yeah? So we'll say that some lottery A is less risky than some lottery B in the sense of Jewitt if and only if the following holds. So if the less risk-averse person prefers the lottery A, it implies that the more risk-averse person also prefers the lottery A to B. Okay? And the reverse doesn't have to hold. Okay? Now, in the binary case, it's actually very simple to tell. Okay, in the binary case, either lotteries can be ranked by FSD, so one lottery gives a higher payoff in each state of the world, okay, or the less risky lottery A is a reduced spread of B. Okay, so simply there is a small distance in between the two outcomes. Okay, and let me show you this in a picture as well. So if you think about two agents with different risk preferences. So here, while this more curvy line represents an indifference curve of a more risky agent. Okay? Now we would like to rank lotteries in terms of their riskiness in this. So there are two states of the world on the two axes. Okay? So if consider these X lotteries, which are, think about this is all asymmetric. Okay? So we can say that lotteries here, both agents will prefer to the X. Okay? And lotteries in this area will be worse for both ages than this X. Okay? Now here, there are lotteries that only the more risk-averse agent prefers to X. Okay? And then we say that these lotteries are less risky than X. Okay? And again, here is the less risk-averse agent prefers these lotteries to X, so we say that these are more risky than X. Okay? This is what this order does. Okay? All right. And then, so next, then, I'll tell you what is the problem with full commitment. Okay, this is just repeating what already exists in the literature, but thinking a bit about Jewitt's order in this context. Okay, so I finally wrote as Vimin's problem. I had Kapos' problem, but I was afraid that is not fine. So,
Can I just ask you a quick question?
Yeah.
Are you assuming that the lotteries can be ranked? I'm just not sure.
So I would like to have a way to rank lotteries in terms of their riskiness, even when not all agents agree on which lottery is better. Better meaning that yields higher expected utility. Okay? And this will.
So you're going to pose single crossing on preferences to get that?
So basically this Jewitt's order is equivalent on a single crossing property on the CDF. Yeah.
Okay.
So basically.
Those indifference curves that you showed didn't respect that.
No, so this can be said for any, how to say, it's not a single crossing on the indifference curve, so these are just indifference curves. I mean, if you look at two risk-averse agents in such a...
You're going to assume that the lottery is wise such that...
Yeah, so basically any lottery here,
Yeah.
compared to here, will satisfy the fact that the CDF crosses the CDF of the X, like to the left or the right, I don't know how to say, right? And you can see that obviously this is a binary case, so this is kind of the easy case, but for more states, it's easier to see with the CDFs.
But you're
okay.
proving this for a general distribution or only for two states distribution?
No, so now what I'm going to show you is for the two states.
Two states.
To have analytical results, we can think about then how we could use the same method to look at more states, or under what conditions we can use Jewitt's order to determine the assortativeness as well. And then I also have an algorithm how to compute things when we cannot have analytical results. Okay, and that would work for more states as well. All right. So this, think about this is a woman's problem. So there is Miss R who is matched with Mr. J, and Mr. J will get the per period utility V. Okay? So for simplicity, you can think of this as just a one period problem. Okay? And so we maximize her utility subject to this constraint that the man has to get V. Okay? Now, if we don't impose anything else, already we impose the resource constraint there, we can get standard conditions. So we will define the ratio of marginal utilities between the two states for an agent as such. So this X will denote the ratio of marginal utilities between the two states for some agent I. And then with this notation, what is the condition for efficient risk sharing is that this ratio of marginal utilities across the two states must be the same for the two agents. Okay, this is just Bosch and Wilson. Okay? So this is the condition of efficient risk sharing within the household here. Okay? And then, so this is existing result in the literature. Under full commitment, we find that the economy satisfies none. Okay? And let me just explain how you can think of this using Jewish children and what's the intuition. Okay? So basically, when the more risk-averse woman is indifferent, then the less risk-averse woman will favor the more do-it risky option, okay, which has greater spread and higher expectation. Okay? And then the question is, who will provide this, this type of lottery? Okay? And, well, so basically, if you think about a more risk-averse man, what he can offer, okay? So he can offer so a higher payment for the same reduction in risk. Okay? So just 1 second. And so then a less risk-averse woman, so a less risk-averse partner will be able to provide this more insurance at a lower cost. Okay? So the less risk-averse woman will have a comparative advantage in providing insurance to the more risk-averse man. That, yes?
If I understand correctly, every couple here pays the same lottery?
Yes.
It's only a question of distribution of the outcome, right?
Of the so all men or women are exactly the same, other than in their risk aversion.
So what would happen if they can choose the lottery? Is it the same occupational choice? They can become criminals or?
Right. So that's a big next step. That's all I can say about it. So this.
So there are no existing results on that? Or?
Yes.
No, there is. Yeah, for perfectly sharing case there is.
Yes, there are few results. Under full commitment, there are 4 results. It's exactly what you expect. I.e., on the one hand, if I'm very risk averse, on the one hand, I love marrying a risk neutral person because she will provide me with a lot of insurance. On the other hand, she's likely to make crazy choice and and it's a trade-off between them. So, and depending on the functional form, you can have one thing or the other. So there is no, you can't go very far. There was someone on the market this year. There was a nice paper in the food organization in the normal case.
Yeah.
Yeah, things get a little complicated if you have non-EU if you have like a rank dependent specification, because then you've got to allow for is it assortative with respect to U double prime or with respect to probability weighting, but that's a different story.
Yeah. Yes. So here we are focusing on this one heterogeneity in this one dimension, and then of course what will matter is the properties of the consumption lottery that then people get out of the couple, basically. All right. So now let me turn to the limited commitment case. So just one more remark. Obviously, this you can think of it as one period or as many periods. You could divide everything by 1 minus beta, and you would be at an infinite horizon model, where in each period the sharing rule would be the same. Okay. All right. So now I'll turn to limited commitment. I'll just simplify my life a little to start with. So we restrict attention to static contracts, as in quote and Ravalian. Okay? So why we do this? So first of all, this is, would say, a natural first step when we want to move from the static model to the dynamic model. And this will allow us to have analytical characterization in a wide range of cases, and also will provide the main intuition. Okay, so what determines associativeness? Okay? All right. So then here is the problem. And so far, it's exactly the same as what I showed you before. So there's a woman, I, who is matched with a man, J, and the man gets the per period utility V. Okay? And I already incorporated the resource constraint. Okay? And now, so a lot of ex post participation constraints have to be satisfied. Okay, so this is one. So consider the state as upper bar. Okay, so the given already the state realization, today the woman gets this utility, and then her expected utility from tomorrow onwards is this, and so this has to be greater than what she would get in autarky. Okay, consuming her endowment of this state, and then whatever then she gets in the future in expectation. Okay, so this is Koshel-Lakota and Thomas and Wall and so on. Okay, and obviously this has to be satisfied in every period, and in all states of the world and for both agents. Okay, so there will be just 3 more of the same constraints. Okay, all right. So then, what will determine the sorting is related to what I say is whose participation constraints are more stringent or more binding. Okay, so so first, suppose that consumption of the woman, say this is C, is less risky in the sense of Jewett than her endowment W. Okay, know that this is. You might think this is always the case since these people are sharing risk, right? So they should, reduce their risk once they are in a couple. This is not necessarily the case. It might be that originally the woman has a sure income, and then the risk sharing is actually such that she will have a riskier consumption than income. Okay, but so suppose now that let's see is less risky in the sense of G than W, then the participation constraint of the less risk-averse woman is more stringent. Yes.
Clarification question. Is this only the case in which you have 2 states of the world, or is it true in general?
Yeah, so if you have more states, then so you have to look at more participation constraints, and it's not obvious that in all states you would have the same result. And actually, when I go to dynamic contracts already, if I have time, I'll talk about what happens if there are sort of one more participation constraint that we have to think about.
Yeah, there's an interaction there between the multiplicity of participation constraints and the transferability of utility, because you can bribe someone to concede on this.
Exactly. So it is. So in the 2 states case, it's so if it is C. What's the transferability exactly? So we only have to look at sort of the one constraint per person, while if you have to look at more constraints, then the question arises whether the ordering of the transferability is the same. And actually, this comes in already just with 2 states once you think about dynamic contracts.
So, Sarolta, there is only one thing. So I understand that the second part, because you are less risk averse, you care less about insurance. But this range, it must be some assumption on the utility function for which, because the default constraint not only depend on tomorrow, the fact that you are penalized by tomorrow, but also by the utility of today.
Right. But so actually, how this actually? Let's go here. So basically, what we can show is that suppose so the woman it has to make a transfer in this as a upper bar state. Mm-hmm. Yeah. And if the so the allocation that satisfies a participation constraint of a less risk-averse woman mm-hmm. will also satisfy the participation constraint of the more risk-averse woman. So this is I hope I said it right. So this is
for a generic utility, that's the only thing is ranking on risk aversion.
Yeah, so the utility functions have to be ranked by Aropret, so you cannot have.
No, that's okay, but that's enough.
Yeah, yes. So in the 2 states case.
Okay.
Yeah? So in other words, the more risk-averse agents can credibly promise larger insurance transfers, and what I mean by insurance transfers is actually the transfer go in this direction, okay, as I described that. So this is one important thing that will determine assertiveness. However, there's another force which comes from efficient risk sharing of aggregate risk, and What I mean by that, so there's partial insurance, there will be some risk left. Okay, consumptions will not be perfectly smooth. Okay? And so this force will always be towards num. Okay, just like in the full commitment case. Okay. Let me just show this to you on a picture. This binding participation constraint. So here, well, this kind of look like indifference curves, but they are not. Okay, so they are. These the participation constraints are just reweighted indifference curve. Yes, I put more weight on the utility of the current state. Okay, so if you take one man, okay, this is just the participation constraint of J in one state, okay, and take this endowment point. The more risk-averse woman will accept so a bigger set of lotteries that make her indifferent between that consumption allocation and the endowment point. Okay? So in this example, what you can see is that it can be that this Mr. J sharing risk with the more risk-averse woman actually can achieve perfect insurance, so you are on the 45-degree line, while this is not possible with the less risk-averse woman. Okay? She would be better off at the endowment point than at the perfect risk-sharing point. Okay? So, so this is how the participation constraint will play a role in sort of who is a more attractive partner. Okay? Somebody who can credibly promise insurance transfer can be a more attractive risk-sharing partner. Okay, that's the whole idea. All right, and so then we have the following two propositions in static contracts. So, so under limited commitment and no aggregate risk, the economy satisfies positive assortative matching. Okay. One remark about this. So. This is only true for any discount factor if there is no aggregate risk at all. If you put some aggregate risk, then we have to restrict the discount factor, because we know from the literature that well, as beta goes to 1, we get to perfect risk sharing, and then we get num. Okay? Or well, num again at this limiting case, it's actually both PAM and num. It doesn't matter who shares risk with whom. Okay? And then second. What we could also show analytically is that if there is a non-negative correlation between endowments, and the following quote, so basically this is a condition on whether the man or the woman makes transfer in a given state. Okay?
So Sarolta, another question, sorry, maybe I didn't understand. What do you mean static contracts?
So static means that from period 1, every time when I'm in state S upper bar, I have a given consumption, and when I'm in S lower bar, I have another consumption.
You mean the steady state of a long-term contract?
Yeah, you can.
No,
exactly. So
there is only one Nash equilibrium, which is auto.
No, right. Yeah. So actually, if you want to look at with two states.
Steady state of a long-term contract. That's what you mean.
Say it again.
You are talking about the steady state of a long-term contract.
Yeah, you can think of it like that. But so in the two states case, we know that the limited commitment model will give you a static thing in the long run, right? With only two states. The issue here is that because of the matching stage, we actually care about the transition. Okay, I can provide more utility during the transition before we hit any participation constraint, and because I need to take care about the transition. It's a restriction to say that I cannot sort of deviate from the long-term contract during the transition. Sure. Okay, so that's, yeah. All right, so we impose some condition on who makes a transfer in which state, okay? This, for a given couple, this is without loss of generality. However, to say that for all couples, transfers go in the same direction, this is not without loss of generality. Okay? And then we get num. So basically, how we can understand these results is to think about the two forces before. Okay? So when there is no aggregate risk, clearly, so for both agents, their consumption will be less risky than their endowment. Okay? And there is not the second force. Okay? no aggregate risk to share. Okay? So there is only the force towards PAM. Okay? And in this case, when there's a non-negative correlation between endowments, under this assumption, the woman's consumption will be more risky than her endowment. Okay? So therefore, there actually the less risk-averse woman will have a comparative advantage in providing insurance. Okay? And plus the sharing of the aggregate risk also goes in the direction of NUM. So there both forces go towards NUM. Yes?
Sorry, I mean, I guess everybody understood that. It's just, again, so in that what you call static contract, which is sort of still dynamic in the sense that you can share risk because you pay depending on S. When data goes to 1, is not full risk sharing?
It is.
So you don't get NUM in that case? Even without aggregate risk?
Yeah, so that's the thing. So actually with no aggregate risk at all, and so full commitment, so when you get perfect risk sharing, everything is equivalent. So then the economy is both PAM and NUM. So that's why we need to...
Well, no.
Okay.
PAM is stable and NUM is also stable and everything is stable.
Yeah,
Okay.
exactly. That's how I should have said it. Okay. So I don't know, how much time do I have? 9 minutes. Okay. So then in the remaining time, I'll say a few words about issues related to dynamic contracts, and then conclude in 2. Say. Okay. So as I said, in this case, it's not enough to think about the static contracts, which would actually occur in the long run with only 2 states, because the transition period matters as well. Okay? So let us think about contracts which can so provide a different transition consumption. Okay? All right. So well, I guess to this audience, this will look quite standard. We think about the value function of the woman. Okay, at time t, having promised v t minus 1 to the man, and the current state is as t. Okay? So we're going to maximize her utility subject to actually providing this promised per period utility to the man. Okay? And while with the restriction that at the time 0 promised utility is the promised utility for the matching. Okay? And then we have participation constraints that are basically intuitively are the same as before, they just look a little complicated, okay, with dynamic contracts. So so I wrote everything already in a recursive form. So you have in this status upper bar, the woman's current utility plus or the expected lifetime utility from tomorrow onwards from this contract has to be at least as great as the value of autarky, okay, or being single. Okay? Again, because I have just 2 income states, I just have 4 of these constraints each period. Okay? So these are the same. Okay? So then what can happen? Okay, and there will be one case that will be sort of tricky. Okay? So so it might be that actually whichever state occurs at time 1, PC will bind. Okay? And then we can say that we are already in the long run at time 1. Okay? So and then there will be these 2 consumption levels in the long run. So there will be partial insurance, but you can say that the contract actually is static in the sense that as before. Okay? Now it might be that at time 1 there is one state where the constraint is not binding. Obviously this will depend on V, the promised utility. Then in the long run, in this simple case, we will, well, with probability 1, we get to the 2 consumptions level, which is the stationary distribution of consumption of the model. However, overall we will have 3 different consumption levels. Okay? And this we can also write as a lottery. Okay? We can analytically compute the probabilities and write everything in expected per period utility terms. Okay? And then there are 2 other cases where in the long run there is perfect risk sharing. Okay? However, with these dynamic contracts it might be that again in the transition period there is a different consumption level. Okay? And well, again we always have to think about that if beta is high enough then we have perfect risk sharing and then just one consumption. All right. Now, I just talk about the case without aggregate risk. Okay? And if we are in the sort of the simpler cases, so when there are maximum 2 consumption levels, we can show PUM as before. Okay? However, once we have already 3 values, okay, so already again the 2 gives us 3, so already there are complications, then we have to rely on numerical methods. Okay, but you can see that in general, and going back to Jewett, it's clear that with a binary lottery, if you look at the CDFs, they cannot cross more than once. Okay? If you already have 3 states, they can cross more than once. Okay? And it is not clear whether the consumption allocation given by my dynamic contract will be such that I can rank the lotteries. Okay? So what do we do in that case is that we can use an algorithm to find stable matchings. Okay? So we take parameters like utility functions, discount factor as given, and we can fix this V prime, which is the utility promised to Mr. J prime, so the less risk-averse man. Okay, then what can we do? So we will find allocations such that 3 agents are indifferent between partners. Okay, so given this V prime, I can compute the optimal contract for the couple Ms. I prime, Ms. J prime, so the less risk-averse agents. Okay, then I let Ms. I prime share risk with Mr. J prime, so J prime prime, so the more risk-averse man, and I make her indifferent between sharing risk with the 2 men. Okay, then from that I can compute the promised utility to Mr. J prime from Ms. I prime. Okay, and then the last step is to check whether the more risk-averse woman would prefer which partner. Okay, I have the V prime from the start. I've just computed the V prime prime. Again, I just have to solve for the optimal dynamic contract and see what is the level of expected lifetime utility that the more risk-averse woman gets. Okay, and then by checking which partner this more risk-averse woman prefers, I get the result whether the stable matching is positive or negative assortative. Okay, so this is how it can be done. And note that actually, so this doesn't really depend on the 2 states case. So there are very sort of standard methods to compute what happens in the long run. So the stationary distribution of consumption I can compute, and then there's a transition period before I hit any participation constraints, so their consumption will be flat. Okay, and so given the long-term contract and the promised utility to the man, of course, it has to be such that this is feasible. I can compute consumption in the transition period. Okay, and so this can be this algorithm can be applied in general. Okay, and then how much time do I have? 1 minute. Okay, so we can basically what we do is we compute 2 examples, changing only the discount factor. So this example I have is standard CRR utility. We first set the discount factor to 2/3 and 2.7. Okay, these are just numbers. Okay, and then we find that first we find negative assortative matching, and with the higher discount factor, you can find positive assortative matching. Okay, so you see that that clearly there is not an analytical result that only one type of matching occurs in all cases. Okay? And actually what happens is that with the higher discount factor, the more risk-averse women sharing risk with the more risk-averse men, they can share risk perfectly on some range of relative Pareto weights, and this gives them so very high utility of sharing risk together. Okay? Now, going back to a previous comment, why we don't have one or the other result in general is because exactly of the transferability of utility in the transition period. Even if we know who has a comparative advantage in providing insurance in the long run, it might be that during the transition period, it's actually the other agent who has a comparative advantage, because those transfers can go the other way. All right. So let me conclude. So what we try to show you is that this negative assortative matching of the literature is not robust to limited commitment, and participation constraints may be actually less binding for more risk-averse agents, and this is why they become more attractive risk-sharing partners. And now, loosely speaking, we say that similar spouses tend to share the idiosyncratic risk, while dissimilar spouses should tend to share the correlated risks. Okay? And there's just some numbers. Okay? Some evidence on assortative matching with respect to risk attitudes. So first of all, using the HRS, where you can categorize people with respect to research, and that you can create 4 categories. And so we are using the table in Mazzocchel's paper. We find 0.14. This is highly significant. So this is for the US. Then from Germany, from the socioeconomic panel, also positive number has been found. And then in another lab experiment, they found no significant result. And then there's a recent paper of Atanasio and co-authors who did a lab experiment sort of in the field where they already know social networks. And what they found is that they actually have endogenous matching to share risk in the experiment. And they know already about friends and relatives. Okay? And they find that for them, they find positive assortative matching. Okay? And for others, no. So you might think, they argue that it's a question of trust as well. And then finally, what I think would be a nice way to test these predictions is to think about basically what happens if over time, say, enforcement technology weakens or the cost of separation decreases. So that would be a force towards more assortative matching. So basically, with a change in beta, we can have a prediction of which the rearrangement of couples should be in which direction. Okay, that's all I wanted to say.